a little late. We had some technical difficulties. So welcome to the Introduction to Utility Power and its Applications workshop. My name is Frankie Mendez. For those of you that don't know me, I used to be active in IEEE the last couple semesters. I held a vice chair position. I'm also known as Mo's counterpart, but yeah. So this little background, I've worked at SoCal Edison for about a little over a year, not necessarily in the transmission and distribution organization, but more on the grid services and telecom side. But we interface quite often. So let's start off with the utility. So list of utility companies, our local ones are going to be SoCal Edison, LADWP, and then a little further down, California is going to be San Diego Gas and Electric, SDG&E for short. And then up north is PG&E, Pacific Gas and Electric. They are kind of struggling right now, but we'll kind of dive more into what a utility company is and how they're not going anywhere, even though they just filed for bankruptcy. So first off, utility companies are technically investment companies. They will be paid no matter if the customers or the users, us, are paying our bills. They get paid at the beginning of the year. So how they work. So the utility company essentially invests using shareholder money and government aid into the grid infrastructure. This is the same for, your water companies and stuff like that. And the way they invest in the infrastructure is through this process called the general rate case. And this happens every 5 years, where we as a utility company submit thousands of pages of documentation on why we need this money and how we're investing it into the infrastructure and what needs to improve. So the last big push for funding from the government was for wildfire mitigation. So that's why you see a lot of SoCal Edison's advertisements and promotions are towards, like, especially with the new squirrel thing, is to kind of gauge and aim towards more awareness for that wildfire mitigation. Moving on, I want to go over kind of the utility departments. A lot of people just think that, especially in the power utility industry, it's just transmission and distribution, but there's so many more organizations involved. So obviously the transmission and distribution one is organizations big, and we kind of like to refer to them as kind of like the football, like, jocks of because they think they run everything, because without them, there's essentially no infrastructure. And more recently, cybersecurity has been a huge addition to the utility sector. Especially with the introduction to like smart grid and grid 2.0, we have a lot more server farms and a IT presence in utility with all the automation and stuff. And believe it or not, we experience millions of hack attempts a day. Because if you think about it, right, if you take out a utility company and infiltrate a utility company, there goes the power for the target, right? And the third sector or organization that I closely hold to my heart, because that's where I worked, is IT, so the Information Technology Organization. First off, I just want to say it's not like your traditional form of IT, like, you getting a phone call and saying, hey, my Excel or my Word isn't working. Can you guys fix it? It's more of like a substation calling you, hey, our satellite communication dropped. like, we need you over here. So that involved us, you know, going to those comm sites and rural substations to kind of troubleshoot what's going on, because we have this data collection acquisition system called SCADA. And this is essentially how we're implementing smart grid and grid 2.0 right now. And just kind of to end off this slide, the stuff that I said about being an investment company in the general rate case, if you guys were to mention that in, you know, kind of like if you're interviewing for a utility company, they will be so amazed, because the general public does not know this. Like, it's one of the things that they kind of brainwashed us in our first month of working there. So moving on. So moving on to like the technical, the transmission and distribution process. So currently right now, the process for the last 50 years has been kind of followed this flow. So you have a generation plant. We'll go over the types of generation in the next slide. And then you have a location or a substation that steps up the voltage for the transmission process, which is illustrated in this blue right here. And then after the transmission process, you have another substation where we step down the voltage, and that's what leads into distribution. Distribution refers to kind of like more of the last mile delivery of power. So you see like those wooden poles and the service lines going to like the customers' homes or resident areas and stuff like that. So the types of generation, they're solar. So SCE owns a solar farm kind of near Vegas. And then Big Creek, which is our hydroelectric generation plant. That's where majority of our generation power comes from. SCE used to have a nuclear plant in San Diego. I don't know if you guys have driven down the 5 and you see kind of like those big old round things right there near the ocean. However, the last 5 years, that's been retired due to some structural integrity issues where it was leaking nuclear radiation. So they've retired that plant, and now they're in the process. I think it's a 20-year process of actually getting rid of it, so it doesn't, the environment doesn't suffer. Proud to say, SoCal Edison doesn't have any fossil fuel generation plants, but they do also have a wind farm, because by 2045, especially in California, all the generation plants have to be non-traditional forms of generation like fossil fuels to kind of combat those years of global warming and stuff like that. Sorry, was there a question? No? All right, so moving on to the transmission process. So there's different types of transmission lines. Obviously, the bigger the lattice structure, the more voltage, because, you know, we want it higher. So no one could, because those lines are live. If you touch that, you're getting vaporized. So right here, I kind of wanted to illustrate this because, again, if you know the difference between, you know, different types of structures in an interviewing process, and the interview sees that, it's going to definitely set you ahead from other applicants. Kind of a funny story. So I don't know if you guys seen like kind of near Rosemead area, how we kind of have more artistic structures like power lines like this guy. The reason for that being is Rosemead and Santa Monica and cities like that, cities with normally more of a high standard of like an economic level, complained to us and said that our power lines were too ugly and it made their city look ugly and non-appealing. So we actually hired a designer to come and design a more artistically appealing power line structure, which I thought was kind of funny. And then I also included, because we talked about that stepping up voltage and stepping down voltage process that occurs at substations. That's essentially the whole function is, I wanted to illustrate that because the transmission process we need, in order to have a successful transmission process, you need that step down and step up stage. Now on to distribution. So this is kind of where, like I said, where we see the power on our end. Without getting into the nitty gritty, like the certain types of, components in the distribution process, because I'm sure you guys will learn that in 315 more in depth. And if not, or if you guys have already taken it, you guys know the difference between a Y and a delta configuration. And then the different types of which lines on the distribution pole are live. But yeah, again, I just wanted to heavily illustrate the whole transmission and distribution process. We have the generation, transmission, or step up, transmission, step down, and then the power that we see in our residential customer side. Because if you understand this at a high level, the low level stuff will come naturally. Low level pertaining to why we have certain components like capacitor banks and conductors and lightning arresters and stuff like that. Before I move on, does anyone have any questions? That was kind of like an information dump right now. No? Okay. So components related to the transmission and distribution process. So I mentioned them a little bit earlier. So we have capacitor banks. Can you guys see my mouse if I hover over it?
Yeah, we can see it.
Perfect. Yeah. So here's your capacitor banks. This is, you'll see them on a few distribution poles or sometimes on substations. And we use these guys to correct power factor. I'll go into more detail about the concept of power factor and why it's important in later slides. But essentially this combats the inductive load, parasitic inductive load that we see. Here's, they call these guys, what do they call these guys? I think they call them bucket. Dang, the name is drifting away from me, but this is a transformer on a distribution line. And here's a transformer. This is called an oiled cooled transformer. You see these guys at like big substations. Right here, another crucial component in the substation and in the transmission process is a fuse. So simple, we use them in our circuits and stuff like that with very low level stuff, but these guys correct circuit management and power distribution heavily rely on these fuses. This will determine whether a power outage is 2 hours or 2 days. And then microwave towers and communication towers you see at substations, again, because of the SCADA process that all utility companies follow. You're going to start seeing a lot more of these, not necessarily microwave, because microwave is moving away because of certain environmental standards, but you'll start seeing a lot more fiber cabling or optic cabling, a lot more almost cell phone looking tower or cell phone devices that kind of look like just white plates with the new implementation of Grid 2.0 and automating with the 5G and stuff like that. And then lightning arresters. These guys are important because, lightning's always drawn to high voltage places, and you're at a substation jumping to 230 kilovolts, and that's a lot of voltage. And these lightning arresters, if a substation gets struck by lightning, will save the substation from blowing up and continuous function. So now moving on to kind of the concepts behind the power transmission process. And this is where majority of the interview questions come from. So the favorite ones and the ones that I've encountered multiple times is, what is power factor? Could you explain it in simple terms? Which will use an analogy that's very commonly used. And how would you improve power factor? And then the next question is, how do we step up voltage? Why do we step up voltage at the beginning of the transmission process? Oh, wow, there's a typo there. All right, so power factor. And my favorite thing, beer. So for those of you that haven't taken 350 yet, power factor is essentially a factor of having real power over imaginary power. And it measures how much power we're seeing. And we'll kind of get more into it with this beer analogy, but power factor ranges from 0 to 1. And as a utility, we strive to have unity power factor, which is a power factor of 1. So that means it's a 1-to-1 ratio. So 1 from transmission to 1 to distribution. And to kind of talk a little bit more about that interview question is, how do we increase power factor to 1, or how to get it close? And I mentioned it earlier, but we add corrective capacitors. So adding a capacitor to a circuit will combat those inductive loads that we're using. Inductive loads add more to the reactive power, as you see in this triangle right here. And to kind of use the beer analogy to illustrate, so think of the power, the real power, the active power, as the feeling of getting drunk, essentially, and how many beers or how big of a beer will get you there. So if you were to buy an $8 beer, right, and you get it, and it's a big mug like this one shown, and half of it is foam and the rest of it is, actual beer, you're going to be kind of a little ticked off, right? So we use this analogy of having a poorly poured beer to illustrate the necessity of having unity power factor. So think of reactive power as the foam, and think of the real power, the substance that we are seeing, as the beer. So we want to have a beer that has minimal foam, high amounts of actual beer, so we could get a little more drunk quicker, right? So we're kind of using that concept and relating it to this triangle, right? So we want apparent power to be as low as possible. So we essentially want the reactive power vector right here to be low or short. And if we have apparent power, which is kind of like that glass, that level, if we have it, by lowering the reactive power vector, the apparent power vector will inherently lower as well. So you'll achieve active power, that level of drunkenness, quicker without having that much foam and having to spend those $8 on that beer. You kind of relate it to almost like a shot. So like adding a capacitor to a circuit is a shot of alcohol, of hard alcohol, rather than having a beer. And if you could correctly describe that and get that point across to anyone, and that's kind of answering that question of, can you explain it in simple terms? Everyone understands beer. You could also even relate it to like a latte as well, having the froth instead of having actual coffee. It will become a concept that could be understood across the board. I kind of went on a lot of stuff right there. Does anyone have any questions? Because this is an important concept that I want to hit home, if anything, on this presentation. Okay, cool. Now the importance of stepping up voltage.
Frankie,
so yeah.
Someone asked in the chat, what is theta exactly?
What is theta?
Yeah.
So that's essentially your power factor angle. I didn't include the other equation in here. So you see this, so your apparent, that angle relates all components of each vector of that triangle. So how can I explain? So remember like right triangles and SOHCAHTOA and stuff like that. So apparent power, reactive power, and active power, which is also called real power, they're all related through this notion of having a power triangle. And solving for that angle, which in your later courses, you'll learn to solve for using voltage and current graphs, will allow you to relate the two and find this ratio of powers of power factor and stuff like that. I should probably check the chat. I can't really see it in presenter view. Daniil, are there any other questions?
No other questions. I'll let you know if there's any questions in the chat.
All right, perfect, thanks. Does that kind of answer the question, whoever asked that? It's just a component in the equation that relates all of them together. Kind of like a, what's the word? Just like a constant or a coefficient that relates the two. All right, so the importance of stepping up voltage. So kind of rudimentary stuff and basic formulas. So for those of you who are kind of new to this, Ohm's law is the equation or formula that started everything, right? So I want to start off with a few questions. You know, have you guys ever seen transmission lines and how low gauge they are? They're small wires, right? And now let's also think how far electricity is, or power is traveling, right? So the closest generation plant that we have is Big Creek, and that's I believe a 6-hour drive. So you're talking about hundreds and thousands of, or no, I'm sorry, it's a day drive, so it's hundreds and thousands of miles away. It's like near kind of like the Rockies. So then using also the analogy of, you know, voltage of a water hose, the current, or the water running through a water hose is the current. The length of the hose is the voltage, essentially, the potential the current has to follow. So we're bound to, using that concept, we're bound to have power losses amongst the line. So using the power equations, right? You know, power is equal to current squared times the resistance. And current is also related to the amount of current. So if you have a small wire, you're not going to get that much current, right? So that's kind of relating to why the wires are super, we're talking about like maybe 22 gauge wire for transmissions, but we're having, you know, 230 kilovolts of stuff running through it. So to kind of go back to those questions, they're small because we want to limit the current, because if we have high current, we're going to experience extreme amounts of power loss through the transmission process. Traveling those hundreds and thousands of miles to meet the customer, we're going to be losing power along the way to heat and other components of resistance and stuff like that. Now, we step up the voltage, right, relating to that other power equation, power is equal to the current times the voltage. If you have high amounts of voltage, that means you have more potential for the current to, or the power to to reach. So if we want to actually make that threshold of traveling those hundreds and thousands of miles, voltage has to be extremely high. You know, the 320 or 230 kilovolts, that's a lot of voltage. And also one thing to hit home, voltage doesn't kill you, it's the current that kills you. That was an interview question that a buddy of mine couldn't answer. Let's see, I saw one on the chat. All right, thanks, Eric. But yeah, so one thing to hit home is best thing to do to avoid power losses is to lower the current and increase the voltage. And now moving on to kind of the power applications. You'll kind of, in your upper division courses, you'll kind of see how this kind of more relates to you guys. But so applications of power and why is it so important? So for those of you who are emphasizing in power, I know there's kind of a stigma. I'm emphasizing in power systems, but there's a stigma behind it, like, oh, it's easy, it's not as hard as, you know, communications or controls or electronics. But if you think about it, power is everywhere. You can't get away from it. You could build the most efficient control system, but how are you going to power it? You need a power systems guy, right? I recommend taking Telebi for any class because you learn extreme amounts of knowledge from that guy. He's extremely knowledgeable in this. My favorite class from him was the EE 450, where you apply the stuff or the concepts of power factor and leading and lagging and having an efficient circuit to design electric motor controlled circuits. A lot of switching, a lot of power supply design and stuff like that. EV charging is another area of stuff where applications of power is so important, especially with Gavin Newsom's new decree is by 2045 or 2030 or 20, I can't remember.
2035. No ICE vehicles.
Yep, and we're going to need huge infrastructure upgrade, and charging is heavily impacted by power concepts, you know, with the whole reactive power and how it could essentially throw off the whole overall power factor of the grid. We're starting to see that right now. I know I was involved on a project at SCE where battery chargers for these things were throwing off. We're adding too much reactive power to the system and essentially overloading a bunch of circuits. Smart grid and wireless communications, that's at the forefront. We'll see new implementations of 5G, and transmission and distribution needs or has a bunch of data that we need to monitor. So that's going to be a huge thing. And again, power is everywhere. You could have if you don't have power, we're just going to have fancy electronic paperweights, really. Like that's all there is to it. But yeah, guys, that kind of concludes my kind of introduction to power transmission distribution. We have 30 minutes. I'm more than welcome to answer any questions, or if anyone wants anything specific that I didn't go over, because I kind of just try to summarize as much as I knew from my experience in my coursework and stuff like that. Don't be shy, guys.
Have you ever worked on any power electronics?
Yes, I'm actually working on it right now for the capstone for power systems. We're
talking about it a little bit.
Yeah, so again, you could have a circuit, but how are you going to power it from line voltage, right? So you're going to need essentially a step down component, which is a power supply, right? So power supply it's essentially the line plus a transformer, and it automatically either gives you a constant voltage and constant current rating, and then dependent on that, you could design a circuit I'm designing a battery charger using power, so a lot of high switching MOSFETs and stuff like that. So that's kind of a new thing to me for my experience in power electronics. But back when I was in Fiat doing system and integration issues or system and integration engineering, one of the vehicle functions that I was in charge of was a lot of the switching control. There's so many electric components that have replaced the mechanical components. And one of the power electronics that I worked with was for the new manual Spider. And it was essentially normal standard cars, manual cars, you have a mechanical gearbox that you switch via clutch. But nowadays, everything's electronic that just sends a signal to an actuator. And understanding kind of at a high level what's going on will help you debug a system from a high level. So what we were seeing is when we were engaging the clutch, it wasn't sending a high enough voltage signal to engage the actual shifter. So my mentor was able to see like, hey, this needs a minimum of 5 volts to actuate the thing. We're only getting 2.3. So we were able to go to the supplier and kind of talk to them what's going on. So it was actually a power with their actuating circuit. So, but yeah, that's kind of in a nutshell my experience with power electronics. Funny enough, Dr. Talebi is an electronics guy, and his area of expertise is power electronics, but he kind of got roped into teaching the power courses at Long Beach. But he has like a fountain. He's forgotten more than I will ever learn type of thing with power electronics. So if you guys are interested in that, definitely reach out to him. He's a helpful guy. But yeah. Any other questions, comments, concerns?
What was the solution when you were working on that SCE project, where you said that the existing grid was getting overloaded? Just kind of my question is more to fix that solution. Do they look at like more efficient energy transmission, or do they look at just generating more power somehow, or do they do both?
Yeah, so it's kind of a combination of the two. So they're actually still working on it. I left midway, started another internship, but it's kind of cool. They actually have like a whole team down in Westminster, dedicated, and they have a cool name too. It's kind of like special ops type thing. And the last time I remember, they were actually thinking of strategically placing battery chargers to kind of act as like a quick fix, because they're seeing way too much reactive power being fed back into the grid. But that was also part of the new general rate case documentation. So they want to essentially upgrade the infrastructure to handle this new reactive power and kind of redirect it somewhere else. Because it's essentially just like a capacitive load, or not capacitive load, it's just more capacitance being introduced into it. And the current infrastructure is built back in the 60s, so it can't handle it. But yeah, I'm assuming that it's still going on. It wasn't like a year fix. It's probably going to be a new thing with the whole infrastructure upgrade and grid 2.0 and stuff like that. Any other questions, guys?
So how do you feel about like Tesla's superchargers, right? Because most chargers use their grid power, which is AC, and then they convert it to DC to power their cars or whatever. And that's usually like very slow and not as fast. But I think Tesla uses banks of batteries already to charge their cars for their superchargers. I think it's either banks of batteries or capacitors to charge their cars. So how do you feel about that?
My unbiased view is I think it's great because it's gonna inherently make charging and the appeal to electric vehicles more common. But Tesla being a direct competitor, I kind of want them to not be as successful because it could essentially threaten my job. So, but I think it's a good thing in the long run for us to kind of transition to more of a renewable, energy, like infrastructure, charging infrastructure, to have the EV presence more predominant. But yeah, improving his charging system and introducing Tesla will kind of affect Zoox in a way, since they also have the autonomy or the autonomous vehicle functionality. But yeah, I think it's a good thing. I think it's a very innovative thing. But yeah.
I got another question then.
What's up?
So 2035, there's the internal combustion engine ban of sales of any model year past 2035 in California. So that means it's only going to be electric vehicles past 2035. But with electric vehicles, you're kind of limited by the range of their battery, which means that you're going to have to, if you want to make a commute from like San Diego to SF, you're probably going to have to stop somewhere and get a charge. But with there not being as much infrastructure, like as gas stations, like there's not as many charging stations as that. How do you think like California is going to handle it? Or, like, what do you think is an approach to that?
So I've actually think in the last 5 years, the infrastructure has increased tremendously. But that's also kind of giving more into having Tesla's not installing them. They're actually hiring contractors to install these. So that's increasing workforce. That's also increasing the amount of skill set needed for electricians. But I think the infrastructure addition is going to increase dramatically. Like, we're going to see chargers everywhere. With that being said, it's also going to kind of need for that grid 2.0 to be, because a lot of people aren't taking that into account yet, and that will probably increase the more need or the demand for power engineers to design a quick fix for the infrastructure upgrade. I know there's a research group at my work right now of meeting up with city officials to kind of start introducing our charging systems into the infrastructure right now. However, our vehicles aren't going to be, readily usable in the next like maybe 10 years, but it needs to happen one way or the other. And I think we have the current supply for it. With all these EEs graduating and stuff like that, but I don't foresee it being an issue. I think the issue with the current regulation and ban is to be more on the societal and humanity side of us normally wanting to, when someone tells us we can't do something, we're going to want to do something. But on the infrastructure side, I think it's no biggie. We could always hire a contractor, and there's a bunch of contractors actually advertising this right now. But yeah.
Along the same lines, I kind of heard from dissenting opinion towards that new law outlawing the combustion engine vehicles in 35 was that there wouldn't be enough there wouldn't be enough like lithium ions or materials basically to power enough vehicles for everyone. But from your experience, does that sound like that's plausible, or is that not really true?
That's actually a good point. I haven't really given it a thought. The lithium ion though is not, I don't think that's a common, so to charge a vehicle, I don't think they're using lithium ions. I know the lithium ion production is going to heavily increase with having the battery itself, but the charging mechanism I think is coming from the line. But yeah, I think a new solution for, they're going to have to create a new battery not using those, because it's, to create one, it's actually more efficient towards the environment, but a lot of people don't talk about that thing. So I know this is just from being in like the kind of the industry. I know Tesla's working on something. I don't know if I could say more to that, but they're working on a new, it's like in the R&D phase of having not utilizing lithium ion and other chemical combinations and stuff like that. But yeah, that is a good point. I haven't really thought about it, but I think the charging mechanism itself is utilizing the line and not necessarily a battery bank for stuff like that.
I think the charging mechanism for like not superchargers is just two-phase power from the line, and then they use that to just plug into your car. And I think the component that like converts like from the AC to DC to charge the battery is located in your car, not necessarily in the charger.
Isn't there also a design for a complete solar? So basically, a supercharger that draws its power from solar energy, or is that not a thing anymore?
So the thing with solar, I don't think the output is great enough. But I know they're still working on it, and I think they just had, I remember reading something on the headline that someone created a solar panel that yielded something ridiculous amount of output. But yeah, there's definitely room for innovation on solar panels. If that appears in the next 5 years, I think we'll see more solar panel influenced vehicles. Or it's just what a lot of people, solar panels work by heating up, so we lose a lot of that. They're talking about putting solar panels on the moon and like using microwaves to transfer the power back down to Earth and stuff like that. There's so much R&D going on with it, but a lot of people don't talk about too, solar panels are toxic waste too, and they have a lifespan, and we're actually coming up on, I think in the next 10 years, a lot of the people who first got solar panels are going to have to retire theirs and essentially dispose of them, but there's not really a good disposable method yet, or waste management method. So for those of you who want to be millionaires in the next 10 years, if you guys could discover something that could utilize solar panel waste, you guys will make it big. But yeah.